Welcome back, class. So we've looked at all of Maxwell's equations in differential form. So one last lecture to wrap up this group of lectures. We're going to take a little closer look at the divergence and what that means, and then from there springboard into an introduction of the divergence theorem. First, we want to take a quick look at another historical background, again looking at people who have in one way or another influenced the field of electromagnetics. The person today is a child prodigy, started his education at the University of Basel at age 13. He worked at the Imperial Russian Academy of Science in the Berlin Academy. He was a colleague of Bernoulli. Surely you've heard of Bernoulli by now in engineering, major contributions to many fields in engineering. Here's an image of this person, and if you haven't been able to guess by now, we're talking about Euler, Leonhard Euler. So what are some notable things about Euler? Well, he authored 75 books on mathematics. His production output was just unbelievable, how much information that he published. And interestingly enough, he went blind for the last 17 years of his life, but this didn't stop him. He never stopped working because by this point in his life, he had memorized all the equations of trigonometry and the analysis at that time that he was working on. And again, that didn't stop him much either because he could solve problems out to 50 decimal places in his head. So I don't know that going blind really slowed this guy down much. He seemed to have incredible ability to memorize and to recall things. Probably the thing we know him most for is for Euler's constant, or E. This was originally derived from and used for cannon calculations. I think it was Napoleon or someone that brought in the mathematicians and was trying to find out how he could fire his cannons more accurately. So I think this came into play there. So just some expressions here are that concern Euler's constant because it's everywhere and it's just an amazing number. This equation right here is considered by many to be the most incredible equation in mathematics, and I think it is definitely a contender. I mean, if you think about it, you have an irrational number to the power of an imaginary irrational number plus 1 is equal to 0. I mean, this is, I could spend a lecture on this and what this means, and it's amazing that Euler was able to come up with that relationship. Here are some of the other expressions for this constant. This is probably the first time it was fully defined because it has to do with interest rates. And so, they were calculating, well, if I have 12 payments in a year at a certain percent, what would be the return on that? And so finally someone said, well, what if we just do this to an infinite number of payments paid infinitely all the time with no time constraints? And that's where the definition of Euler's constant comes from. Some interesting things about this too is, if we look at the function of the curve e to the x, it's pretty amazing because the slope is equal to e to the x, the area under the curve is equal to e to the x, and the height, or the y value, is also equal to e to the x. So many mathematicians give the example of if you had a rocket traveling at a rate of e to the x, the speed, the acceleration, and the distance would all be equal at all times. That's kind of mind-blowing to think about that, but that's why it's kind of important. One interesting thing to note, though, is John Napier actually discovered and published this number first. So Euler really didn't discover it per se, but we owe the symbol for Euler's constant along with the symbol I, sigma, pi, because he was so proficient in writing that he was able to define many of the constants that we use today. One key point here to keep in mind that I think is kind of interesting is that the number E, or Euler's number, is somehow like the number 1, the identity number, in inverse operations for calculus. So, for multiplication and division, 1 is the identity value. 1 times 1 is 1, and 1 divided by 1 is 1. In calculus, e to the x kind of has this distinction of the way it works when we start taking derivatives and integrals. So back to our material today. Again, we're wrapping up part 3. We've looked at all of Maxwell's equations in differential form. We also took a little bit of a detour and looked at Curl and Stokes' theorem. So that's kind of what we're doing again, one more little detour. Since we've talked about divergence in relation to Gauss's laws, we want to take a little closer look at that and then define this new theorem called the Divergence Theorem. So divergence defined or redefined at a point. We now want to take a little closer look at this del operator. I mean, we've introduced that a few lectures back, and I think we've kind of learned how to use it, but we use it to calculate the divergence of a vector. So we want to try to understand what this operator is telling us specifically in layman's terms. So we want to look at how this operator can be used then to invoke the divergence theorem and its application. So first, we want to consider a simple case of Gauss's law for electric fields in differential form. So, of course, we've already defined this, and this just says the divergence of the displacement vector should be equal to the amount of charge related to that or at a point. So again, we wish to now express this at a point using an infinitesimal volume shrinking down to this point as follows. So we'll take both sides and we'll multiply it times this differential volume. And again, we want to shrink that down. So when we look at this, though, this rho, which is our charge density, times this volume is just simply the charge contained in the volume. So this will be the total charge in there, because this is charge per meter squared. This is meter squared, so that'll just give us the total charge contained in there. And so, according to Gauss's law, we know that the summation across the surface that's defining this volume, if we sum up all of the displacement vector normal to that surface, these two quantities should be equal. So that being the case, we should be able to substitute this back in to this equation. So where we had this equation to start with, we see these two are equal. So we're going to take this and substitute in for that. So if we continue with this, we can divide both sides by this differential volume. So when we do that, that gives us this expression here. And so because we haven't technically shrunk this down all the way to a point, this is still only an approximation. So to make it exact, we must let the volume and this corresponding surface shrink to 0. So we will take the limit as this differential volume continues to get smaller and smaller down to an infinitesimally small point. So looking at this expression now gives us an expression for the divergence of D, which that's what we've defined this expression here. Del dot D is the divergence of D. This gives us an expression of this in terms of D itself at a point. So we can see that the displacement vector summed up over a surface divided by the volume as this volume goes to 0 is what we're defining as the divergence at a point. The limiting value to which the flux per unit volume approaches is the value of the divergence of the vector field at that point. So start to see a relationship there. So in physical terms, this basically tells us the difference between how much force is entering a point versus how much is leaving a point, where positive is associated with leaving or expanding and negative with entering or compressing. So we can now use this to apply to illustrating and understanding the physical interpretation of the divergence of a vector in relation to the behavior of electric and magnetic fields. So for example, we want to look at the law of the conservation of charge. So if we do that, we can take this equation here, and this just says that the current density over some surface, some closed surface, and this basically gives us the current over the surface, should be equal to the time change of the total sum of the charge inside the volume created by the surface. And this would make sense, right? So where V is bounded by S, we consider a differential volume delta V. We can rewrite this. So this is just saying whatever current's flowing out of this surface has to be taking away from this charge, or if current's flowing in, depending on the direction, that means charge is accumulating inside the volume. So again, if we take into account this delta V term, we can rewrite this and take it as the time differential then of this total charge, because that's what this is, right? The total charge inside of the volume. And so again, we get this partial of the charge with respect to T as it's changing as the current's flowing times this volume. So with this expression now, we can divide both sides by this volume, which would give us this. So now the change in the charge is going to be equal to the sum of the current over the surface area divided by the total volume. So again, we're going to let this volume shrink to 0 by taking the limit. Of course, if we take the limit on this side, nothing's dependent on the volume, but on this side, we do have it in the denominator. So again, as we've seen earlier, that the left-hand side is the definition of divergence. We looked at that earlier. And the right side is independent of volume. So this equation now becomes this equation here. And this is saying that the divergence of the current density is equal to the time change in charge. So with our understanding of divergence of a vector, what's this equation telling us? Well, in plain English, this simply states that the current density at a single point is equal in magnitude to the change or flow of charge at that point, with respect to time, of course. And the sign or direction of the current is due to whether more charge is entering or accumulating at the point or leaving the point at a higher rate. So that would make sense. So if we have a point, we know there's some charge there. If we have current starting to flow from that point, that would have to mean that the charge itself would be decreasing, because that's what's supplying the electrons to create the current flow. So we can now rearrange this equation just a little bit as follows, and just bringing the right-hand side over. So this is saying then that this current flow, the divergence of the current flow, plus the change of charge over time has got to equal 0. This is an important expression, and it has a name. We call it the continuity equation. It's just another way of expressing the law of conservation of charge. So it's just saying that charge, can't just disappear. We can't create it. We can't destroy it. If there's current flow, it has to be coming from somewhere. So our total charge in the area is going to go up and down, depending on whether current's flowing in or out of that point. And so to graphically express that, if we have charge, if the volume or area that we're looking at is this circle, if we have a certain amount of current going in, but this much coming out, then whatever charge was in here has to be contributing to this to make more flow. Same thing here. If we got more going in, less coming out, then there's charge accumulating in here. And if it's passing straight through, then no additional charge is accumulating or coming out of that area. So we now want to extend from here to derive the divergence theorem, which this isn't like Stokes' theorem. This is a pretty useful theorem when we're dealing with vector calculus, especially in terms of electromagnetics. So to do this, we want to consider an arbitrary volume V in an electric field region and divide this volume into a number of infinitesimally small volumes. And so it looks something like this. So we have this volume defined by S, and we're going to cut this volume up into much smaller cubed volumes, delta V1, delta V2, so on and so forth, where each volume is bounded by a corresponding subsurface S1, S2, S3. And so this is what this would look like to some degree. So now we can start to break this up. So we can sum all these up. So we'll have all these divergences of the displacement vector over these small volumes. And we're saying, well, we can take those separate. We can also integrate all these separately and say that the divergence on the surface of each of these small volumes and add those up, and they should still hold. They should still equal. So here, as we let the number of volumes increase to infinity and shrink down to infinity, and the left side is just then the divergence of d over a total volume, and the right side is simply the closed surface integral of d over s. So since the contribution of the smaller surface integrals interior to s cancel, we can now write this out as that the integral over some volume of the divergence of d should be equal to the summation of d normal to a surface. It's the same surface that's enclosing this volume. This is known as the divergence theorem. And this should prove to be true for any field that we come across. And so again, like with Stokes' theorem, you might run into a problem to where, to get the results that you want, it might come down to an integral that looks like this, and that might be really messy. Sometimes you can do a transformation here using the divergence theorem and do this integral over here instead. It might just make things much more simple, or vice versa. You can go back and forth. Very useful theorem, again, when dealing with vector calculus. So let's look at a quick example then of how this works. We want to verify this, much like we did with Stokes' theorem. So in this case, we're going to have an arbitrary field vector defined for us and has an x, y, and z component. You can see what dependencies there are in each of the components here. And we're going to look at this for a closed surface of a box bounded by planes with x equals 0 to 1, y equals 0 to 2, and z equals 0 to 3. So this is going to form a rectangular looking box. So first we want to determine the surface integral below over the closed surface, our vector dotted with the surface vector, by evaluating this for the 6 surfaces of the box. So to do this, we're going to take each one separately. So for surface 0, this is where x equals 0. We plug that back in. Of course, the x component goes away. We're just left with a y and z component. And we know that our differential surface, since the surface is x, is going to be in y and z in the x direction. So when we take this dot product, everything goes to 0 because we've got ay and az dotted with ax. So this one drops out to 0. If we go to the x1 surface, now we plug in x into here. This one we do have an x component. We still have our y and z component. Same differential surface. Of course, the direction's changed. But this time, since we do have an ax here and an ax here, that dot product is non-zero. We dot that. We get 3 dy dz. We integrate that for the range of z and y, which is 2 and 3. And we come up with 18. Looking at the y surfaces for y equals 0, again plugging that back into the original equation, you can see we still do have non-zero components in all directions. Our differential surface, since we're talking about y, it's going to be in dx and dz in the y direction. We take this dot product, again it's only going to be the y since we're dotting. So again we're left with 3. This time we integrate over the span for 0 and z, which is 1 and 3. Integrate that out and we get 9. We do this again for y equals 2, again plugging y into the original equation we had for a. We still have all 3 components non-zero, same differential surface as before, just with a direction change. So again, with the dot product, just the y terms will multiply. So this gives us negative dz dy, again over the same limits of integration, and we get negative 3. Finally, for the surface z equals 0, we plug in that into original equation, and again we have non-zero for all components. Our differential surface, since we're at z, is going to be dy dx in the z direction. Here the dot product will only be the AZ terms, and so the dot product, we're left with negative 2 dx dy. We integrate that over the limits for the limits for x and y. We get negative 4. And finally, at z equals to 3, plug that into the original equation, we get this. Since the AZs are non-zero, we dot those, and that's what we come up with, negative dx dy, again over the limits for y and x, and we get negative 2. So we've now integrated over all 6 sides. So the total integral then is obtained by adding all these together. So if you go back and add them all up, we get 18. So you can see that took a little bit of time to do that. Whereas we could just do this using the divergence theorem. If we take the divergence of A, so that's del dotted with these guys, so it'll be the partial of AX with respect to X, the partial of AY with respect to Y, the partial of AZ with respect to Z. So in this one we would get 3, and this one we would get 1, and this one we get negative 1 for negative Z. 3 plus 1 minus 1 will give us 3. We integrate that over our limits of integration, which just plug in 3 for this. So we go from 0 to 3, 0 to 2, 0 to 1, 3 dx, dy, dz. It's pretty simple triple integral. Add those up, and we get 18. So therefore, we have demonstrated that divergence theorem holds for this example, and as we stated before, it's been proven it'll hold for all examples involving fields.